Hey friends, Dr. Borole is here. Today we are going to study unit number 2, Transistor and Technology, in which we will see some of the devices, those are the building blocks of electronics, and introduction to the technology of manufacturing electronic VLSI chips. The first device is Bipolar Junction Transistor. BJT is a current control device basically that we will see shortly. Bipolar junction transistor, also abbreviated as BJT. It uses two type of charge carriers, holes and electrons. That is majority and minority charge carriers for conduction of currents, and therefore it is a bipolar device. It's a three-terminal device. It is called transistor because it transfers the electronic voltage and current from input impedance circuit to output impedance circuit, and therefore it is also called as transfer resistance device. BJT have two types, NPN and PNP bipolar junction transistors. Let us see the construction of BJT and its symbol. Here in the first diagram, the constructional aspects are shown. The figure is for the sake of understanding the construction features, which is not drawn to the scale. It consists of two PN junctions. Those are formed by sandwiching P-type material between two N-type materials, forming a NPN transistor. One of the region to which the terminal connected called emitter. The region between the two N-type material called base, and the remaining region is called collector. Emitter region is called emitter because it is a main source of charge carriers providing for conduction, whereas collector collects the majority of the charge carriers, those are injected by the emitter, and therefore it is called collector. The symbol of NPN BJT is shown here. Here on emitter, the arrow is coming out, which indicates the direction of the emitter current. Whereas the third circuit is the equivalent circuit by using two diodes. Similarly, here in the next figure, we will see the structure of PNP transistor. Again, N type of base region is sandwiched between two P type of regions, emitter region and collector region. In NPN transistor, the majority charge carriers are electrons and minority charge carriers are holes. Whereas in PNP devices, the majority charge particles are holes and minority charge particles are electron. The symbol of PNP transistor is shown in this figure. Here there is an arrow on emitter again, but the direction is going inside. That indicates the direction of conventional current flowing through the emitter. The third figure here is shown, that is the equivalent circuit using PN junctions. base to emitter PN junction and collector to base PN junction. The actual construction is shown in this figure. The cross section of the BJT is shown there. During the fabrication process, they will first create a N-type material, this one shown here. In this N-type material then, by the doping process, the trivalent impurity is added to create a P-type of island, as shown by green color. After fabricating the P-type of base region, again impurity type will be changed to pentavalent impurity to create a N-type of island in the P-type of base region, and therefore we get NPN structure. We will see the doping levels, those are kept for NPN and PNP transistors. Here the first column indicates the doping level and the width of various regions. Second column indicate emitter, third column indicate the base, and fourth column indicate the collector. So doping level of emitter is kept highest. That is, if we consider the NPN transistor, then emitter is N-type and the doping concentration for emitter is kept high. The doping concentration is kept low for base region, and for collector region, the doping level will be moderate. This doping level will be decided so that the BJT can provide the current amplification. The width of various regions are shown here. Width of the emitter is kept moderate. Base is the narrowest portion amongst the three, and collector is widest. Collector is normally wider for high voltage BJTs because width of the collector is proportional to the collector to base breakdown voltage. For large breakdown voltage, the collector width required will be larger. Base is the narrowest portion because the amplification factor beta of the device is the ratio of collector current to base current. And when base is narrow, the base current value will be lower, and therefore amplification factor will be increased. Let us see the operational aspect of transistor, bipolar junction transistor. Let us consider the transistor under unbiased condition. That means no external voltage is applied. As we know from the construction, there are two PN junctions. For the sake of simplicity, we will consider the NPN device for the discussion. Here you will see N type of emitter area, P type of base area, and N type of collector area. This figure, the base is shown somewhat wider. Here, the figure is not drawn to the scale, as we have just discussed that base is the narrowest portion. Collector is the widest portion and emitter is the moderate size portion. Here, to show the internal working, we have changed the scales. Now, here in N type of material, there are majority charge carrier as electrons and minority charge carriers are hole. Whereas in P type of region, there are holes as majority and electrons are minority. And in collector, again, electrons are majority and holes are minority. The minority charge carriers, as we know, they are due to the thermal agitation or thermal excitation, which actually creates the minority charge carriers because of breakage of the covalent bond at elevated temperature. At 0 degree Kelvin, there are no minority charge carriers present in BJT. Okay. Now, since in N type of emitter, the electrons are majority and P side in the base, there are holes in majority. So there is a charge difference. Due to that, the electrons are diffused from emitter to base, leaving behind positive immobile ions around the base region. Similarly, from base, holes are diffused to emitter, which leaves behind the N type of immobile ion on the base side. And therefore, it forms a potential difference and electric field created by immobile charges. There is no free charge available in this region, and therefore it is also called as depletion region, as we have seen in PN junction theory. Here we have seen that this depletion region will be widened in base more than the emitter because base is lightly doped, and therefore in the lightly doped material the spread of the depletion region is more than highly doped area like emitter. Similar thing happens around the collector to base junction. From collector, the electrons are diffused to base, leaving behind the positive immobile ions on the collector side of the junction. And holes injected from base to collector leaves behind the negative ions on base side. And therefore, there is a formation of a depletion region around the collector to base junction. This happens when no voltage is applied. The process of diffusion will be stopped when the field of diffusion will be counterbalanced by the field of depletion region at steady state. Now let us see various operating regions of BJTs. Here we will list the operating regions of BJT and we will study these regions in detail whenever we will see the characteristic of BJT and operating point of bipolar junction transistor circuits. There are three regions of operations for BJT. First is called active region or linear region. In this region, the BJT can be used as a linear device or amplifying device. The second region is cutoff region, in which no current flows through the BJT and therefore it is acting as off switch. And the region in which this happens, it is called as cutoff region. Saturation region. In the saturation region, the current flowing through the BJT R reaches to the maximum value in the circuit. And therefore, the device goes in fully on state and therefore it is acting as a on switch. The operation of the BJT in this region called saturation region. Now operating point or Q point. Operating point is designated by a letter Q and therefore it is also called as Q point. The operating point is defined as the VCQ and ICQ value in the collector circuit and VBQ and IBQ value in the base circuit. The transistor biasing. Transistor biasing is nothing but a method of setting the Q point in the base circuit and the Q point in the collector circuit. Biasing basically establishes the Q point in the input section of BJT circuit, that is most of the time base to emitter junction circuit. So establishing voltage and current relationship in the input circuit can develop the corresponding voltage and current in the collector circuit and decides the value of VCQ and ICQ in terms of circuit components. So function of the biasing circuit is, in short, to establish the operating point for BJT in input circuit and output circuit so that it can be operated in the desired region out of the three regions we have discussed. The biasing can be done by using external DC power supplies. Here, for the sake of simplicity, we have used the batteries as external power supplies. But this can be any DC power supply present in the circuit. If you see the BJT, the input junction or junction between base to emitter is called as BE junction and the voltage drop across it is denoted by VBE. And junction between base to collector is called as CB junction and voltage across it will be VCB. The voltage between collector and emitter is denoted by VCE. Now, the biasing can be done by using the batteries that is shown in this circuit. For the sake of simplicity, the current limiting resistance components are not shown in this diagram. Here we are using the NPN transistor and let us suppose that we want to bias the device in active region. For that purpose, base to emitter junction should be kept in forward bias and base to collector junction should be kept in reverse bias. That can be done by VEE supply for base to emitter junction and VCC supply for collector to base junction. The input circuit is basically base to emitter circuit and output circuit is collector to base circuit. The current which is flowing through the emitter is input current, that is denoted as IE, and the current flowing through the collector terminal, that is IC, that is as output current. Here the battery shows how biasing can be done to keep base to emitter junction forward bias and collector to base junction reverse bias. Various biasing conditions of base to emitter junction and base to collector junction for operating the device in various region is shown here in the table. For active region, we have seen emitter to base junction should be forward bias and collector to base junction is in reverse bias. Whereas in cutoff region, emitter to base junction should be reverse bias, as well as collector to base junction is reverse bias. So therefore, both the junctions are in reverse bias, so no current flows to the device, and therefore operating point will be located in the cutoff region by adjusting the appropriate voltages of VEE and VCC. In saturation region, emitter to base junction is in forward bias, whereas collector to base junction is also operated in forward bias, and therefore current flowing through the device is maximum. This biasing is done in saturation region again by adjusting the value of supply voltages VEE and VCC such that the operating point lies in the saturation region. Again, here note that the current limiting resistance RB and the load resistance RC, which is not shown in the diagram. Those are always required to establish the base current or emitter current in input side circuit, that is base to emitter circuit, and RC is required to limit the collector current in collector to base circuit. Now, operation of the NPN transistor from the physical construction perspective. Let us see what happens inside the device when we apply the various biases to the junction. In forward active region, let us see the operation. So here the internal structure of BJT is shown. So here in the diagram, we will see emitter region, base region and collector region. The corresponding depletion region of base to emitter junction is shown, whereas the depletion region of collector to base junction is shown. Since base to emitter junction is in forward bias, the width of the depletion region around base to emitter junction is smaller, whereas collector to base junction is in reverse bias, therefore width of the depletion region is more here depending on the strength of the collector to base junction supply applied. Now here it is a NPN device. So we will see to keep the base to emitter junction forward bias, we connect emitter area to negative of the power supply and positive area base to the positive terminal of the power supply. Here these external wires are shown in which the electrons are flowing. Okay. Now, when base to emitter supply is applied and collector to base supply is applied for reverse bias condition in the collector to base region, due to forward bias between base to emitter junction, the electrons are pushed and forcibly cross the base to emitter junction due to the electrical potential of base to emitter junction. So electrons, those are the majority charge carriers, those are injected from emitter to base. Whereas holes are forcefully injected from base to emitter. So therefore, since electrons are majority, so major portion of the emitter current is coming from when these injected electrons reach in the base region, some of them are combined with the holes in the base region and form the base current. Since the emitter is highly doped, large number of electrons reaches to the base under force, means they are drifted from emitter to base. Where base is lightly doped, therefore the recombination rate in the base will be very small and therefore base current will be very small. Let us consider the hypothetical example. If 100 electrons are injected from the emitter Around 5% electrons constitute the base current and remaining electrons are attracted to the collector due to the reverse bias field around collector to base region, and therefore collector collects around 95% of electrons, and therefore the name collector. So therefore small change in the base current results to large change in the emitter current. When more and more voltage, forward bias voltage is applied to base to emitter junction, more and more electrons are injected by emitter to base. And therefore, more and more electrons are getting collected by the collector. So therefore, small change in base to emitter voltage gives rise to large increase in collector current. The same thing is shown here in the diagram too. Here, the diagram indicates the charge particle and their direction of flow. The majority charge particles, electrons, those are shown, those are injected from emitter. Here, few of them, say around 5%, those are constituting the base current and remaining goes to collector, and therefore three currents are formed. In the emitter, the current form is denoted as emitter current. The current in the base region is called as base current, and the current in the collector region is called as collector current. And from the diagram, we can say that the current through the emitter is a sum of base current and collector current. Therefore, we can write IE is equal to IC plus IB. This is the relationship of currents for BJT. Here, in the next diagram, somewhat elaborated view of the currents are shown. In this diagram, we consider the minority charge carrier flow also. So, here electron flow is shown by the gray color arrow. That current in the emitter, electron current in the emitter is denoted as IEN, which is divided as ICN and IBN. Whereas, due to minority charge carriers, there is a flow of current between base to emitter junction, that is denoted as IEP, and here around the collector junction there is a minority charge current which is flowing, that is denoted as ICO. Since the minority charge particles are very less compared to majority one, we can conclude that under the normal operating conditions, the current in NPN BJT is mainly constituted by electrons in emitter region and collector region. Operation of PNP transistor. Here the structure is shown and the operation is exactly similar to NPN device, only since the region, emitter region and collector region type is changed, therefore the charge particles are also changed from electrons to hole as a majority charge particles. And therefore here also the current which is injected by emitter to the base will be divided in two parts. One constitute the base current and remaining will be collected by the collector current. So we can write IE is equal to IC plus IB here. In PNP devices, we will see the biasing. Here P type of material is connected to positive terminal of the battery and N type of base is connected to negative terminal of battery, so that base to emitter junction will be forward bias. Similarly, collector to base junction, we will see the collector P type of material is connected to negative of the battery and N type of base is connected to positive of the battery V.B.C. so that collector to base junction will be in reverse bias. So once the biasing is done, that establishes the current IE is equal to IC plus IB in the external circuit. Now let us denote and see the nomenclature of representing the various electrical quantities in BJT circuit. Here in the first column, the relationship IE is equal to IC plus IB is shown with the capital letters. Normally DC quantities are shown with the capital letters. Since IB is much less than IC, we can therefore say IE is approximately equal to IC. Whereas in the second column, we will see again the relationship IE is equal to IC plus IB is shown with small letter. This indicates normally small letters are used for indicating the time varying quantity or signal quantity. Whereas in the third column, we have mixture of small case and capital suffix. It indicates AC plus DC quantities. Various transistor configurations. Since transistor have three terminals, it can be configured in the input circuit and output circuit with respect to a common terminal. Whichever terminal is common out of the three terminals decides the configuration. According to that, there are three configuration results: common base configuration, common emitter configuration, and common collector configuration. In common base configuration, base terminal is common between input and output circuit. Here, in common base configuration, you will see that VEE supply is used to provide the biasing for base to emitter junction. The current which is forming the input current is denoted as IE, and in the output circuit, the current is denoted by IC, that is as a output current, and which will be established by the biasing source VCC in collector to base output circuit. Here the PNP transistor circuit is shown, in which again VEE is establishing the input circuit voltage and current, and VCC is establishing output circuit current IC and VCB, where in this circuit RC and RE are used to limit the input circuit current and output circuit current. By using the value of RC and RE, we can establish the appropriate Q point in our emitter to base circuit and in the output circuit. The current relationship in common base configuration. From the figure shown under operation, in common base region, the collector current IC is observed to be IC injected plus ICBO, where IC injected is the current established by injected charge carriers from emitter to base, and those are collected by the collector. Whereas ICBO is the reverse leakage current of base to emitter junction due to minority charge carriers. The important parameter in CB configurations are: common terminal is base, input current is IE, output current is IC, input voltage is VBE, output voltage is VCB, between collector and base it is taken. The current gain is alpha DC. The other parameters we will discuss later. The current amplification factor or current gain in common base configuration is denoted by a letter alpha or alpha DC, and that is defined as ratio of output current to input current. The output current is IC in this configuration and input current is IE. And we know that IC is less than IE, therefore current amplification factor alpha is always less than 1. The common emitter configuration now. In this configuration, the emitter terminal is common between the input circuit and output circuit. The input is applied between base to emitter, and therefore input voltage to the configuration is VBE and input current is IB. The biasing supply for the input circuit is denoted by VBB. Whereas in collector circuit, the collector to emitter voltage VCE is the output voltage and collector current is the output current. This collector current will be established by the biasing supply VCC and the corresponding value of RC. Since emitter is common in this configuration, it is called as common emitter configuration. The current gain in common emitter configuration is denoted by a letter beta, and it is defined as the ratio of output current to input current. In common emitter configuration, output current is IC and input current is IB. Since IC is much greater than IB, the current amplification factor beta is always much greater than 1. Now let us estimate the relationship between alpha and beta. We have IE is equal to IC plus IB. But IC is equal to beta into IB from the above relationship of beta, which is a ratio of IC by IB. And therefore, we will substitute IC is equal to IB into beta. And therefore, from this, we take IB common. So in bracket, we will get 1 plus beta DC into IB is equal to IE. But we know alpha is equal to alpha DC, that is equal to IC by IE. Substitute the value of IE here, you get IC upon 1 plus beta DC into IB, and that is equal to beta DC upon 1 plus beta DC, because IC by IB is beta. From this equation, if we reshuffle this equation and take beta on left hand side and push alpha on the right hand side, then we will get the relationship of beta and alpha in terms of alpha. Or we can use again our current relationship of emitter current equal to IC plus IB to derive the expression or relation between beta and alpha in terms of alpha. We can see beta is IC by IB. But in the denominator, IB is nothing but IE minus IC. Take IE common from the denominator, we will get beta equal to IC upon IE in bracket 1 minus IC by IE. Here IC by IE is alpha, and therefore the equation becomes beta DC is equal to alpha DC divided by 1 minus alpha DC. For the value of alpha, which is always less than 1, if it is assumed to be 0.99, then it will make beta as 0.99 divided by 1 minus 0.99, that is around 99. And therefore, we have seen even though alpha is less than 1, beta will be much greater than 1. So that's all for it today. We will meet again in the next lecture. Till then, goodbye.